Hello, this is Dr. Kessler. We're going to continue with our lecture about basic statistical concepts. Our focus for the rest of this first lecture is really on talking about ways to take a set of data and to be able to pull out information about that data's characteristics. Very useful for helping people answer questions when all they have is raw data. So we're going to continue, and we're going to go through a number of techniques designed to enable us to examine the descriptive characteristics of data. And so let's begin. Descriptive measures for categorical variables. Now you'll recall that nominal data is non-numeric, and for most of it, most of the types of categorical variables, you have repeating values like male or female. Some respondents are male and some are female, so there's some number of male respondents and some number of female respondents. So there's two categories, male or female, and there's information that we don't know yet about the categorical variable called gender. So when you have a categorical variable and you want to be able to examine it, you can do that in certain ways. One is you can count the number in each category, and that's what this bottom here says. And so let's imagine that we've got a variable called gender. You can see it's listed here on the right hand on the side. And we have two categories. We have male and we have female. So if we were to go to someplace on our spreadsheet, and I will have a separate video on how to use Excel, so be sure to tune in to that separate video. It'll be available on YouTube. So I would set up, I would just type in a place on my spreadsheet, categorical summaries. I would type in gender, count, and percent. I would type in the letter M in this cell and the letter F in this cell. But in these two cells here, I would actually begin to use some of the Excel features that enable me to describe how many male observations are in my data. And so if you look here on the left-hand side, you can see what I would put into that cell. And you always start off a Excel function or an Excel formula with an equal sign. That tells Excel, here comes a formula, or here comes a function. And one of the functions that Excel knows is called count if. So if you put equal count if, Excel's going to know when it encounters this cell that it's supposed to look in columns C2 through, that's what the colon means, C75. And now let's assume in this spreadsheet that over in column C, in cells C2 through C75, are listed all of my gender observations. And let's suppose I want to count just the M's that are in cells C2 through C75. And that's how the formula would look. It has to be coded fairly precisely like this. It has to have parentheses. It has to list a begin cell and an end cell with a colon in the middle. It has to have a comma. It has to have these double quotation marks. And then what you're trying to count inside those quotation marks. So in this case, although this wouldn't work for C2 through C75. But in the actual formula here, the Excel spreadsheet counted 6,889 instances of M in that column for that variable. And then the formula was coded here, except for M inside the quotes, it's F inside the quotes. And so in that case, the females in that column were 7,172. Now you're going to note here that that's almost 8,000 records. Now it'd be a pain to have to go through and count them by hand when you have 13,000, almost 14,000 records. There's almost 14,000 rows in the table. It's a very big table. It's a lot of data. You do not want to count it by hand, and so you're able to do that. You're also able to, using a percent function, which I haven't shown on the slide, you're able to show that these two values represent 100% of the equation, and that 68, 89 is 49% of all observations, and 51% of the observations are female. So these are other functions that I'll show you when I do my Excel presentation. Alternative method of coding. Another way to do this would be to, and I mentioned this earlier, in the column here, in column D, you have males and females. Well, if you're able to convert those by adding a new column called dummy gender, and then go through and convert the females to zeros and the males to ones, and again, I'll show you in Excel how you would do that quickly as opposed to typing them in for 14,000 rows. You can do the same thing. You can come here and easily do a count of your ones and a count of your zeros. Now, this idea of creating a dummy variable is not so important here because we have the count if function. But later, if we want to run statistical analyses looking at perhaps the salary for males and comparing it to the salary for females, we would need these ones and zeros in order to run a statistical method. Descriptive measures for numerical variables. So we talked about categorical variables, and we talked about using the count if function or creating a dummy column, a dummy variable. Now we're going to talk about numerical variables. There are many ways in Excel and in statistical package to summarize numerical variables. And when you have numbers, it's a lot easier to deal with. One of the key ways of presenting, looking at, and analyzing raw data is to use measurements like we showed before, and also to use charts. And when you have numerical data, you can present that in charts, and it gives sometimes a picture is better than words. To learn how variable values are distributed, we have to ask a number of questions. We have to ask ourselves, when we're looking at a particular variable, what are the most typical values in this column? How spread out are the values in the column? Now, when I say what are the most typical values in the column, it's sort of like a little hint that we're going to be talking about, what's the average value in this column? How spread out are the values? Because more spread out, less spread out, kind of makes a difference in terms of how you interpret the data. What are the extreme values on either end? I'll talk about that. Is the chart of values symmetric around the middle value if we have a normal distribution, or is it skewed in some direction? These are all very important and useful ways to look at your data to be able to communicate to others the characteristics or the description of your data. And so we'll go into each of those in a bit of detail. In a particular case here, we mentioned earlier baseball salaries. If we wanted to learn how the salaries are distributed across all 2009 Major League Baseball players, and let's assume we have every player in our database, you can see in column D we have salaries. And so we want to ask ourselves, sort of what's the smallest salary, what's the highest salary, and what's the sort of the middle salary, the average salary. So we want to really understand salaries of all the baseball players, and we want to be able to look and examine the salaries in a lot of different ways. We have to appreciate or understand different ways that statistics enables us to look at that particular variable. And so we're going to cover in this lecture measures of central tendency. We're also going to cover how to find the minimum value, the minimum salary, the maximum salary. We're going to talk about how to organize the data according to percentiles and according to quartiles. We're going to discuss measures of variability and measures of shape, because these are all very important concepts when you think about your data and you want to take your raw data and sort of prepare a memo or communicate, maybe a PowerPoint presentation to communicate to others about the data. These are your sort of your basic starting points. This is the beginning use of statistical methods, and it's called descriptive statistics. So let's talk first about measures of central tendency. We're going to discuss this concept of a distribution curve. And we're going to spend most of our time assuming that we have a normal distribution of data. It's not always true, but we're going to make that assumption for quite a bit of our conversation. Now, in order to discuss central tendency, most of you have heard about average in your lives, and the statistical term is mean. And mean is often calculated as either X bar, you see on the right-hand side, or Y bar, depending on what you're trying to do. And there's also the concept of a sample mean, meaning that the data represents a sample and not the entire mean of the entire target population. There's the population mean, where the data set really represents the entire population, and that's denoted as mu, this little symbol here. And notice for Excel data sets that we really don't need a statistical package. We can calculate the mean very simply by using the average function in Microsoft Excel. And I'll show you that in another lecture because we don't want to take the time now. Any of these functions is equal average or equal COUNTS. You can always go to your browser and you can do a search on how to format those functions in order to be able to use them in the spreadsheet. Measures central tendency median. We've already talked about mean, which is average, but sometimes we may want to look at the data in a different way. And median tells us sort of what's the center of all of our observations, where's the middle. And so when the data is arranged from smallest to largest, we can ask ourselves, what is the middle point on the data? And so sometimes it's useful to want to know sort of what the middle of all of our data is. You'll find that you'll use mean a lot more than median, and you use mean and median a lot more than you'll use mode. Mode is the value that appears most often, and so mode might be, in the case of looking at the U.S. population, the mode may have been European American for a long period of time, and we may find, as we start to collect statistics in the U.S. over a period of time, that Hispanic American may become the modal value for population type data. So mode, and it does say here that mode is not very useful, especially when you have continuous data, because you're not likely to get a lot of repeat values in the data set. So mean, median, and mode are your measures of central tendency. Mean is the one you're most likely to use in most cases. You can also find other dimensions of your data. You can find the minimum value of data. You can find the maximum value of data. And you can calculate the average of data. Now, I've included at the bottom here, embarrassingly, I track my weight compulsively. And if you see in column C, that's my daily weight scores. And so on column A, I have the date. Column C, I have my actual weight. Something in column B, but I just did it. Then over in columns H, I, J, and K, I calculate the highest value, the maximum value of my weight, the minimum value of my weight for a given year, and the average weight for a given year. So if you look in 2015, you'll see that my average weight, using this formula on the left-hand side, was 212.4. If you look in column J, my minimum weight, it was 203.6, and you look at my maximum weight, it was 221.8. So you sort of see my weight variation in 2015. You also notice if you look down in 2014 that I was a lot smaller in 2014. So you'll notice in 2014 my average weight was 199, my minimum weight was 188, and my maximum weight was 218. So these are very powerful functions that we can use in Microsoft Excel to examine data, to be able to pull out the smallest value of a variable, the largest value of a variable, or to be able to calculate the average value of a variable. Now you'll notice that since weight is a ratio type data element, it's ideally suited for these type of functions. I didn't mention percentiles and quartiles. Now for any percentage p, the percentile is the value such that p has all values or less than it. Well, what that basically means is if I tell you the percentile value of a number, you know that that's, if it's 50%, and it's 50% of the values are less than, and 50% or more. For quartiles, the data is divided into 4 groups, so I can say that my values are 25% of my values are in the first quartile, 50% are in the second quartile, and so forth. So we can use minimum, maximum, percentiles, and quartiles to report about characteristics of our data. Now, instead of measures of central tendency, we also have measures of variability, and we have range, which is important or useful measure to measure the maximum value minus the minimum value, which really gives you a crude measure of how much variation exists in your data. But in reality, you're not going to use either the range or the interquartile range. What you're more likely to use is called the standard deviation. And so we do have these measures of variability, one being variance, and you can sort of see how that's calculated here. And you can see this note here. It says hard to interpret variance numerically because it's in squared units. And then you see for standard deviation, a more natural measure, which is the square root of variance, is a very useful measure. To calculate standard deviation in Excel, we have a standard deviation function, or the standard deviation key function for the population, which again I can go over in my Excel briefing. Now we're going to talk about standard deviation in a little more detail because in terms of measures of variability, it's the most commonly used and the most important variable. So what is the standard deviation? Well, on the previous slide I gave you sort of a formula for standard deviation. Well, we generally tend not to use the formula. We generally tend to get the data out of Excel, or we tend to get it out of a statistical package. But we need to interpret what we're seeing. And so in order to understand the standard deviation, you really need to appreciate that if I had a normally distributed bell curve, and in the middle of the bell curve was the mean or the average, the line running right through the top of the curve, down to the x-axis, represents the mean. Our standard deviation tells us for any particular observation, any particular measurement, how far away from the mean the actual observation lies. And these are three very important rules about standard deviation. If your standard deviation is one standard deviation or less, that means that your value is that 68% of all the values are just one standard deviation from the mean. So your value lies within the top of the 68%, who are closest to the average. A lot of times that's a very good thing. We notice that 2 standard deviations from the mean, if you get to 2 units away from the average, 95% of all of our observations in a normal distribution reside within 2 standard deviations of the mean. And then when we get to 3 standard deviations of the mean, we can appreciate or recognize that 99.7% of all observations lie within 3 standard deviations of the mean. And therefore, only 2.3% of observations would be beyond 3 standard deviations. Now I'll ask in activities that I ask my students to do, I'll say, well, is it a good thing or is it a bad thing to be -3 standard deviations from the mean? I said -3, -3 standard deviations. So what that means is that 3 standard deviations are negative on the negative side, on the left side of the mean, means that you get probably, you're very different than the average, and in a negative sort of a way. And then on the other hand, if the 3 standard deviations positive from the mean, that means you're probably in the top 2 to 3% of everybody in what you're doing. And so this idea of understanding standard deviations and how to interpret the standard deviation value is extremely important. And as you can see at the bottom, it says most variables that we deal with, that you will deal with, probably are normally distributed. All right. We've been talking about normal distribution, sort of the bell curve, but the idea of skewness or kurtosis are very important to understand as well. Sometimes you'll have a curve and it has a top is not in the center, it's off to the left or it's off to the right. And this is referred to being skewed. The curve, the distribution of your variable, whether it's test score or whether it's age or whether it's income, is not sort of in the middle, it's sort of to the left, which means most people make less than middle salaries. Or it could be skewed to the right, where most people were making more than the typical salary. And so when you get skewedness, you have to sort of appreciate what the data is telling you about the variable that you plotted. And as you look at it, you have to say to yourself, what factors are causing the data to be skewed to the left or to the right. And so now in the baseball players' salaries data that I was discussing earlier, if I had one player who was making $35 million, while most of the other players are making maybe $1 to $2 million, that could potentially cause a skewing to the right, because you've got one person making $35 million. And so it's very important to find these reasons or factors that are making your data not be normally distributed, and ultimately, as we'll see me say later, to get rid of those outliers, those data points that are causing your data to be skewed, because they can certainly distort any kind of analysis you're trying to do about most of your observations. Kurtosis has to do with the fatness of the distribution tails relative to the tails of a normal distribution. A distribution with high kurtosis has extreme observations, and so just like we talked about with skewness, what we really are trying to do here is to get things to be normally distributed. And so when you see bell curves or your data distributed in a way that makes it be skewed or to suffer from kurtosis, you have to take action to clean your observations so that you can get rid of the skewness or kurtosis in the data. So how do we want to, what methods can we use to look at our data? Well, we can certainly use a histogram, which is the most common chart for showing numerical variable distribution. Now there's this concept in histograms called binning, and what that does is it sort of divides your data on the x-axis into a certain number of groups. Now when I run a statistical package, most often the package will give me an option to let the software determine how many bins to create. And I almost always will say, I'll default to the automatic option. And so there are reasons, and we'll get into those reasons at some point, about why you might want to force the bins to be some number that is particularly of interest to you. In general, histograms are great for showing the distribution shape. Is it symmetric or is it skewed? Does it have kurtosis or not have kurtosis? Another numerical measure is a box plot or a Whisper plot. And you have to take some time and study this image that you see in the bottom right-hand side. But this is an alternative chart type for showing the distribution of your variables. And the reason that a box plot is very useful is because it'll show your extreme outliers, whether they're positive or negative. So if you look at the bottom, you can see on the far right-hand side an extreme outlier and a mid-outlier. And when you run a box plot, it shows you that you've got some outliers in your data. You can go find those outliers, take them out of your data set, and rerun so that you have no extreme outliers, so you'll get your normal distribution, so that you can rely on using statistical tools, because they depend on a normally distributed set of data. So this is an example of a histogram, baseball player salary distribution using histogram. And so you can sort of see that with this one variable that you have, that you look at this variable, and for salaries in the bin, and again the computer picked the bin, where the middle point of the bin is $1.881 million, there's almost 600 players making $1.88 million. Remember, I defaulted, so the values across the bottom were picked by the computer. Now I may decide that I don't want this number of bins, and I may go in and set up my own bins, but that's okay. So now we come down to the next category here, and we see that $4.845 million is the next bin, and there's slightly over 100 players who make almost $5 million. When you look at 7,809,000, there's fewer number, 10 million or fewer number, 13 million, you're down to maybe 20 or 25 players, 17 million, very few, 20 million, 22 million, and then it gets blank. 25 and 28 have no members. And then if you look at the 31.5 million, you see one player out there. That is your outlier, and we saw that on the previous Whisper plot chart. Okay, this is the box plot example that I was showing you earlier, but it's a little easier to see. Notice that this diagram in the upper right-hand shows you sort of what a Whisper plot is all about. It shows you your interquartile range. It shows in the first quartile how many folks are there. It shows the middle of the range. It shows the mean of the range. It shows the third quartile here on the right-hand side, which is refers to the upper whisker, and you can see your outliers. And those outliers have to be dealt with if you're going to run statistical tools later on the data. Time series data, I mentioned time series data before. Time series data is data over time, and when you chart data over time, as you can imagine, what you're going to see is you're going to see on the bottom, you're going to see dates. And then what you're going to see on the left-hand side are values, and you're going to be able to observe those values in the context of time. So you can sort of look at when things have gone up or down or whatever over time. So when we want to look at like economic data, we like to look at it over time. We want to look at crime or similar type events over time. We use time series charts and time series data. Again, I have an entire lecture on time series data. I already mentioned outliers before. It's a value or observation that lies well outside the norm. As you can see, not everyone agrees. How do you exactly define an outlier? Well, you have to use your judgment. But when you run a box plot or Whisper plot, and you see outliers, it's really important, as this last bullet says here, to deal with those outliers, to get them out of your data set so that your data is not unusually distorted or skewed by a single or very few number of variables. That's the end of this presentation. I hope it was helpful. I will continue lecturing on other basic concepts of statistics. What's important in this lecture is to understand that typically most students will start, especially in classes, by being given a data set and being asked to make sense out of that data set. And so the measures of central tendency and the measures of variability and these visual charting tools are very important to be able to understand. Many textbooks have been written about these concepts and these tools, but it's essential if you're going to prepare a report or prepare a presentation about the data, that your very first step is to dig into data to understand each of the variables, whether it's numeric or non-numeric, to be able to do some counts of categories, to be able to look at the distribution of the data, and to look at the standard deviation characteristics of the data. And once you're able to do that, you're in a position of having strong descriptive statistics about the set of data. And once you do that, then you can begin to formulate some research questions, and we can begin to use more advanced statistical methods to dig into our research questions.